This lecture we'll learn what exactly the TF stack method does when it's applied to a list of tensors. The last practical demo, we read in a bunch of images and then resized them to all be of the same size. In this demo, we'll perform some further transformations on images so that we get a hang of working with them. All the code for this demo is present in the file Image Transformations with Coordinator. Open up that file and follow along step by step. You'll find in this demo that we've already seen a huge chunk of this code before. Most of this involves reading in all the files, using threads, using a coordinator to manage these threads, setting up these file names in a queue, and using queue runners, which spin up the threads that the coordinator manages. We're still working on the two images that I've set up of my dogs, that is the original image list. Make sure you change it and update it to point to your images. The image names and the number of images that you have might be different. Set up a queue of the image names using string input producer in the tf.train library. We use the tf.whole file reader to read in images, one entire file at a time. Instantiate a session using a with statement, and a lot of code here is the same as before as well. Notice at the very top we instantiate the coordinator which coordinates the loading of image files. We set up queue runners which spawn off multiple threads that is coordinated by this coordinator. We then have a for loop which iterates over the images that we have. We use the image reader to read them from the file name queue. We decode these images as JPEG files and then we resize them to be 224 by 224 length and width. These are RGB images, which means the shape of the image tensor is 224 by 224 by 3, where the last 3 represents the number of channels in that image. One for R, one for G, and one for B values. Color images have 3 channels. Once we have these resized images, we can perform transformations on these image tensors. The flip up-down transformation flips the image upside down. The image will be flipped along the horizontal axis. Let's perform another transformation here. We'll call tf.image.central crop. This will choose some portion of the image specified by the fraction that you pass in. Here the fraction is 0.5, that is 50%. Central crop will preserve the middle or central 50% of the image and crop out the rest. Let's now call session.run on this image and print out the shape of the resultant array that is stored in image underscore array. Image underscore array is a numpy array of height, width, and 3 as the number of channels for that particular image. Calling tf.stack on this numpy array will convert it to a tensor. If the original numpy array had dimensions 224 by 224 by 3, the tensor will have shape 224 by 224 by 3. Print out this image tensor so you can see what it looks like and append it to a list of images. Every element in this image list is an image tensor. At the end of the for loop, call coordinator.requestStop and coordinator.join threads to wait for all images to finish loading and finish processing. Now, if we want to convert this list of image tensors to one tensor which represents all these images, we can use tf.stack. The tf stack operation applied to a list of tensors where every tensor in the list has a rank of r will convert it to a single tensor of rank r plus 1. The list of images that we pass in, each tensor in that list has a rank of 3. This will convert it to a single tensor of rank 4. The images tensor is a rank 4 tensor where the first dimension is the index of an image and the remaining dimensions represent the images themselves. When we have a single tensor representing multiple images, writing out image summaries also becomes easier. You can apply the tf.summary.image operation on the tensor which represents a list of images and write out the summary to summary writer. Let's execute this block of code and see what the individual steps look like. Notice that we have two tensors representing images. These are both of rank 3. These are 112 by 112 by 3. Why 112? We started out with images that were 224 by 224, but the central crop operation, which preserved only the center 50% of the image, converted these to 112 by 112 images. And when you apply the tf.stack to the list of images, you get one tensor with a rank of 4. The first dimension, which has the number 2, indicates that there are 2 images in this list. The remaining dimensions are the dimensions of each image, 112 by 112 by 3. It's important to note that a single tensor can be used to represent multiple images only if all those images are of the same size. If the size or the dimensions of the individual images are different, they can't be represented in a single tensor. Let's run TensorBoard and see what the computation graph looks like. Click on the link, go to the Graphs tab, and here is the very complicated graph of our processing. The more processing we add, the more TensorBoard has to do, which explains why the graph looks like this. The Images tab should show you that a single list of images have been written out, and it contains both images of my dogs. They have been central cropped and flipped upside down. And coming back to tf.stack, which we had referenced at the beginning of this lecture, if you feed tfstack a list of tensors where every tensor is of rank r, it will convert it to a single tensor of rank r plus 1. All the tensors in the list will be represented by one tensor.